All right, time for Math Tidbits number 6, where we're going to talk about derivatives. Okay, so to begin, and I'm going to switch to blue, it's a little bolder. This should be review for anybody who has had calculus, and hopefully a sufficient introduction to those who are in Calc 1 right now and haven't had it before. I want to begin this discussion a little bit unconventionally by considering the relationship between two variables that is linear. All right, so if I have a variable p and a variable q of some sort that are related linearly, then if I plot p versus q, I will expect a straight line, right? The slope of this line is constant. Okay, so if I take any finite interval, let's say from there to there, then given a linear relationship, I will expect that the rise delta p over the run delta q is a constant. Okay, that's what it means for these two variables to be related in a linear fashion. The equation that one writes for such a case as this is something like p equals m times q plus b, where this is the slope. That is, this is delta p by delta q. And this is the intercept of the on the p-axis. That is, it's the value that p has when q is 0. So if you like, there's where b is. Okay, so it is that p equals b, where that line crosses that axis. Okay? So that's a linear a linear case. Again, just to emphasize, if I take another interval over here, that is, let's say delta q prime in width, then this little amount here, delta p prime, will also be related by delta p prime over delta q prime equals m. Okay, that's what we mean by a curve having constant slope. Now, a nonlinear graph, let's suppose variables g, that's not a g, that's a q, g and h are not linearly related. Then, and just for the purpose of illustration, let's make it do something like that. So this is the function g plotted as a function of an independent variable h. And it is manifestly the case that the slope here is definitely not constant. So again, if I take some finite interval here, from here to here, let's say, call this delta h, and call this amount delta g, those in that location, those values are not going to be the same as, let's say, delta h prime here, where that decrease in g, delta g prime, is going to be we can see immediately that delta G over delta H is not the same as delta G prime over delta H prime. So the slopes there differ, right? The slope is not a constant. And so there's no relationship that we can write between G and H that has some fixed kind of slope. Delta G over delta H differs depending on where on the curve we sample. So no hope of some kind of G equals MH plus B. However, other powers of H might apply. Okay. So the slope is changing, but we can investigate the slope as a function of the independent variable H. And that's certainly interesting to do. So let's consider part of this curve. So we'll consider part of the curve that's going like this. And let's consider a point on the curve that we call A. And I want to know what's the slope there. Well, one of the ways that we can get at the slope there, and again, this is not new for those of you who've had calculus. For those of you that haven't, this is going to be new, but hopefully understandable. If I want to know what the slope of that curve is at that location, I can start by saying, well, how about this is a point GH, right? So this value is G at H. And let's go over here, and we will call this difference delta H. And so at that location, the value of G is G at H plus delta H. And the approximation we can make to the slope at this location would be to draw this line, and that would indeed be a line that could be written in terms of a slope. And we would say that delta G divided by delta H is equal to G at H plus delta H minus G at H divided by delta H. And that would be an approximation to the slope at this particular location A. So this is an approximation for slope at A. All right? Not necessarily a very good one, but it's certainly one that we could employ. Now, if I wanted to do a little bit better, I could make my delta H a bit smaller and draw this line and say, yeah, okay, for this delta H prime, then this is G at H plus delta H prime. And I've got another approximation, a better approximation of delta G over delta H prime, as it were, it being G at H plus delta H prime minus G at H over delta H prime. Okay, that's a better approximation. It's not perfect, because I'm still dealing with an approximation over this finite interval and not exactly what's the slope at that point. Well, the logical end of this is to say the best approximation is to take the limit as delta H goes to 0 of this delta G that we've written over delta H. Or the limit, just to be complete, the limit as delta H goes to 0 of G at H plus delta H minus G at H over delta H. This is what we call this. This is the slope of the best approximation, which is the slope of a tangent line. The tangent line which runs and connects to the curve only at that point of interest. This is what we define as the derivative dg dh. Okay? So, just to summarize on the back side of this, the slope of the tangent line at A is dg dh evaluated at h equals A. Okay, so the line which touches just barely and is touching right at that point A, it's the slope of this line that is equal to the derivative. And again, that's the limit. We will use this definition a few times in this video. I wanted to go to x already. I shouldn't. Delta h goes to 0 of g at h plus delta h minus g at h divided by delta h. As delta h shrinks down to 0, so does the numerator. But there is a limiting value that this ratio has, a limiting value of this slope. All right? So let's consider a practical case. Just to illustrate this, let's suppose we take the function y equals ax squared plus bx plus c, where x is an independent variable, a, b, and c are constants. And I want to know what's dy dx. Okay? Because at each point we can define a value. At each specific value of x, we can define a particular slope for this tangent line. And this is clearly going to be a nonlinear curve, so that slope is going to be changing all the time. Well, we can let x be equal, so we let x be equal to x plus delta x, and then form delta y divided by delta x, and take the limit as x goes to as delta x goes to 0. That's what our task is going to be. And we're going to do this explicitly just to illustrate the method. So y at x plus delta x is simply going to be equal to a times x plus delta x squared plus b times x plus delta x plus c. Now I'm going to square out that binomial and multiply through the value of a. So this will give me ax squared plus 2ax delta x plus a delta x squared plus bx plus b delta x plus c. Okay? I can then recognize that I've got the usual y at x here. So this is y at x, and then plus a couple of pieces that involve delta x. So plus 2ax plus b times delta x, and then a final term that is proportional to delta x squared, like so. Now if I want to form delta y divided by delta x, I can do so. Notice that here's it's y at x plus delta x minus y at x over delta x. So if I take y at x plus delta x and subtract off y at x, I'm going to be left with 2ax plus b times delta x plus a times delta x squared. Divide that by delta x. All right, well that, if I divide the delta x out, I'm left with an expression of 2ax plus b plus a times delta x. That is the expression delta y divided by delta x. The last step, according to our algorithm here, is to take the limit as delta x goes to 0 of delta y over delta x. And when I do this, I get this term, the a delta x term, will go away, and I'm left only with this, 2ax plus b. That is the derivative of y with respect to x for y equals ax squared plus bx plus c. Okay? So, you may recognize, those of you that have done calculus before, that there is kind of a mechanism that can be employed here, a mechanism for taking derivatives of powers of x. And I do want to note this, but only after doing another case. So let's do another case. Suppose y equals x cubed. I'm going to run through this a little bit quicker than I did the previous. Let's suppose y equals x cubed. Then delta y, we're going to calculate, is equal to y at x plus delta x minus y at x. That means, or that is, rather, x plus delta x, quantity cubed, minus x cubed. I'm going to skip one step here and do the whole cube in my head, because I know the way to do it. You can take an extra step if you like. That's x cubed plus 3x squared times delta x plus 3x times delta x squared plus delta x cubed. And now I need to subtract y of x, so I subtract x cubed. So I've got left that piece. Now, delta y divided by delta x is equal to 3x squared plus 3x times delta x plus delta x squared. Okay, if I just take this expression up here for delta y and I divide that by delta x, that goes away, that power gets reduced to 2, or to 1, that power gets reduced to 2. And now if I take the limit as delta x goes to 0 of delta y divided by delta x, that's going to make those two terms go away. I'm going to be left with 3x squared, which is the derivative of y with respect to x if y equals x cubed. Okay? Now, if you have done calculus before, you know how easy it is to take the derivatives with respect to x of a power of x. All right? Namely, we now sort of have a mechanism, because I've shown you a couple of examples, You can prove it exhaustively, actually, which I won't do. But if y is a power of x, then the derivative with respect to x of y is as follows. So if y is equal to x to the nth power, then the derivative of y with respect to x is n times x to the n minus 1. You just take the n, decrease it by 1, and plop an n out in front. That's really, really easy. It is true, in fact, for any n. That is true for any n. Okay? So, taking dy dx and using simply the mechanical method, you can find easily that the two results that we got before, namely that if y is ax squared plus bx plus c, then dy dx is 2ax. Let's just look at this explicitly. The derivative with respect to x of ax squared plus bx plus c. I take the first term. A constant will always come out the front. All right. So maybe I should have generically said, well, yeah, I'll write it down in a second. I've got 2 times a times x, taking care of this term. This term, x to the n minus 1 is going to be x to the 0. That's 1. So I'm just going to be left with b here. Okay? The general rule, again, is if y equals a constant a times x to the n, then dy dx is equal to na times x to the n minus 1. Okay? Again, works for all n. Now, I want to introduce one other derivative that will become important later on. And that is, what if y is equal to the sine of x? What is dy dx? Again, we'll use this later, but I wanted to play with it now. Just to again illustrate this method, especially for those who are not totally familiar with derivatives and or those whose skills with derivatives are somewhat rusty. So let's just start as we have in the past with delta y equals sine of x plus delta x minus sine of x. Okay, same method exactly. We need to use a trig identity here for the sum of two angles, or for the sine of the sum of two angles. So you'll recall from your pre-calc or trigonometry days that sine of theta plus phi is sine of theta cosine of phi plus sine of phi cosine of theta. So we can write delta y as the sine of x times the cosine of delta x plus the sine of delta x times the cosine of x, and then subtract off sine of x. All right. So now what we're going to be doing, we're going to be taking the limit as delta x goes to 0 of delta y over delta x. So that means we're taking the limit as delta x goes to 0 of, and let's write down, I'm going to take common sine x and multiply by the quantity cosine delta x minus 1, and that's divided by delta x. And then I want to split off a term, the limit as delta x goes to 0 of cosine x times sine delta x over delta x. Okay. Now, I'm going to use something that I'm going to prove in a subsequent video. Okay. I'm going to utilize the fact that for small angles, and when we're talking about cosine delta x here and sine delta x here, eventually we're going to be taking the limit as delta x goes to small, so these are going to be perfectly good approximations. Sine, so for small angles, little delta. Sine of delta is approximately delta. And cosine delta is approximately 1, but we augment that with a second term in the series expansion that we'll talk about in another video, 1 minus delta squared over 2. All right, so in this case, then, that means sine delta x goes to delta x, and cosine delta x goes to 1 minus delta x squared over 2. So this whole term here becomes 1 minus delta x squared over 2 minus 1 all over delta x. And this guy becomes delta x over delta x. Well, no matter what delta x does, the ratio of delta x over delta x goes to 1. And in this all is going to boil down to delta x over 2. So now, dy dx, which is equal to this limit, delta y over, got ahead of myself, delta y over delta x. This is the limit as delta x goes to 0 of sine x times delta x over 2. Well, that's a big fat 0. And as delta x goes to 0, delta x over delta x goes to 1. So this is the limit as delta x goes to 0 of cosine x. So this is just cosine x. And y'all already know that, who know a little bit of calculus. If y equals sine of x, then dy dx equals cosine of x. Now similarly, and we can do the same calculations, same exact method. Maybe it would be worth your while to do just for giggles. If y is cosine x, then dy dx is equal to minus sine of x. All right? So, to close out this session, this edition of Math Tidbits, I guess, for common functions and things that come up in physics all the time, it's worthwhile having memorized all of these, where y of x is given here and dy dx is calculated. So if y is a times sine, stepping back a little bit, a times x to the nth power, then dy dx is na times x to the n minus 1. We did that today. And if y is sine of x, then dy dx is cosine of x. And if y is cosine of x, then dy dx is minus sine of x. Another couple that we didn't do but could do by exactly the same method, e to the x, the derivative of e to the x is, watch it, e to the x. That makes the exponential function something very, very interesting, that the slope of the exponential curve is exactly equal to the function value at the point of interest. And the inverse of this, the log, natural log of x, this also we will encounter a lot in physics. Its derivative is 1 over x. All right, so that is it for this particular episode of Math Tidbits for today, and we will talk again very soon.